Yes, I have. Yep.
Okay, then let me just kick it off. So welcome everybody to this colloquium. I'm happy that several people are attending. I got some worrying away messages from several PhD students who are on holiday this week. Apparently that's a good spot for vacation. So, but we're still very happy that Heletje van Staden is giving a talk today. She recently became an assistant professor of management, let me read it, in the supply chain management area at UCD, University College Dublin. We are extremely happy to have you here. And she will be talking about the effect of multi-sensor data on condition-based maintenance policies. So please just go ahead. Heletje said she's happy to answer questions in between if there's confusing things or things need to be clarified. Otherwise, we will have a question round at the end of the colloquium. So thanks for being here and please go ahead.
Okay, great. Thank you. Thank you for the introduction, Niels. So can you see my screen right now?
Yes.
Okay. Thank you. So thank you for the introduction and the invitation to present today. So yeah, as Niels said, I recently started in Dublin, and the work that I'll present today formed part of my PhD with my supervisor, Robert Bute. So it's joint work, and we published it in the European Journal of Operational Research. So if you have any other related questions, the paper is also available online. So to kick off, usually when I do this presentation, I kind of make a case for why condition-based maintenance is necessary, is important. But given the audience today, I think everyone here is working on something related to maintenance. So we're all a part of that. And the biggest probably contribution to research in predictive and condition-based maintenance today is the rise of Industry 4.0 and relevant technologies, such as the Internet of Things. We have cloud computing, machine learning. We have all these technologies at our disposal, which means that suddenly we have access to a large amount of information to help us make better decisions in maintaining our systems. But we have also seen that a lot of companies that are implementing predictive maintenance are not necessarily realizing all these benefits that have been predicted to come with predictive maintenance, such as reducing costs, reducing downtime. And usually we find that a big reason for this is that the data that we do have access to is not necessarily good data. And sometimes it just provides us with a partial idea of the underlying state of the system that we are trying to measure. And that kind of inspired the research that we did in this paper. So we took the approach and said, well, let's say we have access to different sources of information that if we do use this information, we can make better predictions of our system. But we might not necessarily own the equipment, the sensors, or related technologies that produce the data. So sometimes we might have to pay for it. And we then asked ourselves, but do we always need access to this data, or can we just devise a strategy where we acquire it as needed to maintain our systems and ultimately minimize our maintenance costs and improve reliability? So that brings us to an example scenario for our research. So let's say we are in charge of maintaining a single asset on a factory floor. And this asset can have sensors installed on the machine that measures different condition information, such as, let's say, temperature. And we refer to this information as internal sensor information. And we say internal because we own the machine, we own the sensor, so any of the data we get is at our disposal to use in measuring the actual condition of the machine that we are trying to maintain, or that we are trying to maintain optimally. But then on this factory floor, there might be numerous other sensors acting in the environment. And if we were to have access to this information, we could improve our predictions of the actual underlying state of our system. And these sensors could even be seen as a technician being dispatched to the factory to determine the quality of the output, which we could then translate back into the actual state of the system. So that is the setting that we are looking at today. And the two main questions that we investigated is, okay, given we have access to external information, but because we do not own these sources, we have to pay for it. So it's costly. And given we can have access to it, when do we actually want to have access to it? With the main aim of minimizing the long-run maintenance cost rate of this machine. And if we can do that, what is also the additional value of more informative external information to the decision maker? Now, usually when I present this work, we immediately get two questions. So firstly, what do we mean by more informative? And simply, so to give a bit more background of our model, we have our machine or our asset that we are maintaining, and we assume that it can either be in one of two states, a healthy state or a warning state. And so we know we can't observe these states directly. But in order to get a prediction of the underlying state of our system, we use what we refer to as the belief state. And the belief state is simply the probability that our machine is in the warning state. And then, so we know we have access to internal information that allows us to determine this probability. But if we were to pay for external information, it will provide us with a better indication of the true state. So we formulated that mathematically, and practically it looks as follows. So we relate the underlying unobservable system states to our belief state using what we refer to as a state observation matrix. And that simply gives us the probability of when we observe a particular outcome, our system is either in healthy or the warning state. And the main difference between these two matrices is we assume the external sensor is always more informative, because otherwise we don't want that information because we pay for it. And more informative means that we are always more likely to observe low observations from the external sensor than we are likely to observe low observations from the internal sensor, as we can see in the matrix over here. And we are also, if our external sensor is more informative, we are also more likely to observe high observations from the external sensor than the internal one. So for instance, in the blue box, we can see if we observe observation free, we have 99% certainty that the system is in the warning state, whereas for the internal sensor, we are much less certain. So this is how we base our mathematical model. So, and if anyone has questions about informativeness or what I'm talking, you are very, very welcome to just interrupt me and ask questions, as Neil said. So the second question that we get is, okay, so we have this belief state. That is the probability that we are in the warning state. Now, if we have that, how do we actually update it? And use Bayes' theorem for that. So we model it as a Markov decision process. And this belief state pi is simply the probability that we are in the warning state given a particular observation. And we calculate it as, firstly, the likelihood of observing that observation multiplied by the probability that we are in the warning state, which is these parentheses over here, and we divide it by the probability of actually observing observation y. And this belief state is updated after every action that we take. So how does that actually work? I'll explain it by means of a bit of a diagram. So we model our problem as a partially observable Markov decision process. It's partially observable because we don't know what the exact underlying state of our machine is. And it's an MDP, which is simply, as we know, like a sequential decision problem, and then ideal to model maintenance. So if we look at how this pure MDP works, we're going to start in our initial belief state. And whenever we start, we assume that the machine is as good as new, which means that pi, or our belief state, is going to be equal to 0. We then have free actions, one of free actions that we can take at any given decision epoch. And these actions will always be based on the current value of our belief state. So action 1, we can decide we don't want to pay for external information, we don't want to perform maintenance, so we just let the system run as normal, we don't do anything, but we do get internal information. Action 2, we decide, okay, we don't want to maintain, but we want to increase the reliability of our predictions. So we pay for additional information. And action 3, we stop the system and we perform maintenance. So what happens if we choose actions 1 or 2? So we first choose action. The model continues, and it's going to transition to one of the two unobservable operating states. So it can be healthy or warning, or it can transition to an observable failure state. So whenever the machine fails, we assume we can see it has failed. It's observable. And this transition happens according to our reliability function over here. So after the system has transitioned, if it has not failed, it means it's either in a healthy or the warning state. We then obtain, at the end of the decision epoch, an observation. If we chose action 1, we will receive an internal sensor observation. If we performed action 2, we will additionally receive an external sensor observation, and these are from one of the two possible sets that we can obtain these observations from. If, however, the system transitioned to a failure state, we stop the system and we perform immediate corrective maintenance. We update our belief state according to that probability, and we continue the process again. So that is the idea behind our Markov decision process. And we actually then model, so what does these actions actually look like? So we obtain 3 different value functions for each action. The first term in action 1 is the cost that we will incur in that decision epoch if we chose to do nothing and the system failed before we had time to take another action. So if you recall, our aim is to minimize the long-run average cost rate. So we use the lambda minimization technique to change our value functions into an additive function. So this lambda over here becomes our average cost rate. We multiply it with the mean time to failure of the system in that particular decision epoch, and we add our continuation value function. And this little guy over here is simply the probability of actually observing a particular observation y. So that's our action 1. Action 2 looks very similar to action 1. The only difference is we now incur an external sensor cost related to that particular sensor, and our observations come from a different set than from action 1. And finally, if we determine our belief state is high enough, we stop the system, we choose action 3, and we perform preventive maintenance. So these are the 3 actions available to us. we then take those actions and we can actually show that the optimal maintenance policy for this problem consists of at most 4 regions. And so I'm not going to go through the mathematics of the theorems. They are in a paper, but I'm also happy to talk about it afterwards if anyone has questions. But the gist of the theorem is very easily explained by means of a figure. So first, let's dissect what we have here. So on the horizontal axis, we have our decision epochs in running hours. And on the vertical axis over here, we have our belief state. It's between 0 and 1. The higher the belief state, the higher the probability, or the larger the probability that our system is in the warning state, which means the closer it is to failure. And the different colors in the graph that you see over here refer to our different actions. So whenever we are in a white zone, we do nothing. We just continue on with our internal sensor information. If we are in a light gray zone, we pay for external information. As soon as we reach a dark gray zone, we stop the system, we maintain. And we can obtain these different zones by means of 3 different thresholds. And we refer to this as the lower sensor threshold, pi L. Pi subscript U is the upper sensor threshold, and pi subscript M is the maintenance threshold. So how would that work? So for instance, let's say we start at decision epoch 0 with a new machine. We are in the white zone, we don't do anything. As soon as our belief state crosses the lower sensor threshold, we start paying for external sensor information. And then it is possible that we can reach a second white zone. So usually this comes across as a bit counterintuitive, but we can define it as the marginal benefit of external sensor information that we can get in this zone is actually outweighed by the cost of paying for that information. Because basically by the time we reach the zone, we know we are going to stop the system to perform maintenance soon. So it's not necessarily worth it to keep paying for external information. And therefore we save a bit of money, and we only maintain again, well, the first time, once we reach the dark gray zone. So that is how our policy works. If we look at our value functions, so if you look at this figure over here, this is how the cost of the different actions will change. And it also shows us how if we go back to the previous slide, how we find this 4-region policy. So the line that's always at the bottom here, that is our optimal action. That basically refers to our optimal action that we want to take. So we can see for a belief set of 0 again on the horizontal axis, we will prefer the red line because that will give us the lowest average cost until we reach the crossover of the internal and external sensor information value functions. And after that, we start paying for information. We will stop paying for it briefly, and then as soon as the green bar or the green line is the lowest, we'll pay for information. So that is how we actually determine the thresholds. And usually we can see if our policy is a 4-region policy, the difference between the external sensor information and internal sensor information in cost is actually not that much. It's actually quite close. So that is how we obtain our thresholds. But then we also show in theorems 2 and 3 that if we keep the cost of external information constant, but we increase the external sensor information, this 4th region will disappear, as we can imagine. And because our external sensor becomes more reliable, we will start paying for it earlier, and we will also start postponing the performance of maintenance. So that's what we all know, right? If we know exactly in what state the system is, or we have a very good idea, then we can only maintain until we really know it is necessary. So that's theorems 2 and 3. And then the nice thing with that is we can also translate the results into a decision maker's willingness to pay for external sensor information. So in the previous slide, we showed what happened if a sensor cost remained the same. But what if these costs actually change as well? So what do we see in these figures? First, G over here refers to our original external sensor that we used as in a base case in the paper. And then we explored 3 additional external information observations or sensors. So this is G2, G2 bar, and G3. And the main thing for you to know about this is G3 it provides us with approximately perfect information. So if we have access to sensor that provides observation matrix G3, we basically believe we know what the underlying state of the system is. The difference between these two over here is that we are actually indifferent at different points between these matrices. And simply that means our requirement for informativeness does not hold between these two matrices. So currently, for a low sensor cost of 25, we actually prefer information from sensor 2 because it gives us better information when we are in the healthy state. We'll see that in the next slide. But then, as the external sensor costs increase, we actually start to prefer information from G2, as we can see over here. The average cost is now less for information from G2 bar, than from G2. And we can also, as sensor costs increase, we can see how our optimal policy changes in response to that. So whereas in the first place, for low sensor cost, we almost always pay for it. As soon as it becomes more expensive, for our first external matrix, which is the least informative, we almost never pay for information now, simply because the value we get out of it is not worth it for us. And the same happens as we continue to increase our external sensor cost, and eventually we will stop using external information altogether. And what's nice about this figure is, as a decision maker, we can use it and we can see, okay, this is our cost value trade-off. When should I pay for more information? When should I not? And also, how much should I pay for it to really get the benefits out of the sensors? So in this example, we showed how the optimal policy changes if we have access to only one sensor at a time. So only sensor G, G2, G2 bar. But can it maybe be beneficial to have access to more than one external sensor at a time? And that is what we investigated in the next slide. And first, we want to see, okay, what happens if we add additional sensors? So over here, we see the actual matrices for the different sensors. So D is our internal sensor information. G, G2, G2 bar are our external sensors. They are increasing in informativeness, but we are indifferent between the last two matrices depending on the cost of the matrices and where we are. And for this particular case, we're also going to set the sensor cost at increasing cost, simply because if you look at the last sensor, we know as soon as we observe observation free from this sensor, we basically know we are in a warning state, so we're willing to pay for that information if we think our machine is critical. How does that affect our value functions? So in our analysis, we can say, okay, if we have access to more than one sensor at a time, which means we have more actions available in our model, we obtain at most one additional threshold. If the informativeness of the sensors are close together, we might not even obtain an additional threshold, and we might not even use all the sensors in our model. So this is how our optimal policy changes. The threshold at the bottom shows when we use a different sensor. So we start off with the red sensor, which is our internal sensor, which simply means until our belief state is just over 10%, we don't pay anything. We just continue as normal. And then as our belief state increases, we start paying for information. So when we pay for the light blue matrix, that is G2 over here, we see we want to pay for it because it has actually the highest probability of being in a low state if we observe, in a healthy state, if we observe observation 1, than all these matrices. So we prefer external sensor G2 for low belief states. But as soon as the belief state increases above this threshold over here, we will probably start observing higher observations from then onwards, which means that we stop preferring sensor G2 because it's still it's not as accurate as G2 bar for higher observations, and it's actually equivalent in accuracy to our first sensor, which is cheaper. So from this point on, we're going to pay for information from sensor G. And until we reach the next threshold, where now we believe, okay, our machine is, the belief set is quite high. It might fail anytime soon. I want to get reliable as possible predictions. So then I'm willing to pay more to get information from sensor G2 bar. So that all looks very nice, and it really gives a case for having access to more data. But if we actually plot the whole value functions of every action, we see in this particular case that the value add of additional external sensors may actually be quite small. So even though here we can clearly see how our sensors will result in different actions as our belief state increases, we actually see that these value functions are very, very close together. And if we consider the change in average cost, then we also see that these are actually quite minor. So adding sensor G only improves our average cost by 0.2%, whereas adding our almost perfect information will improve the long run cost rate by up to 2%. So for a decision maker to want to have access to different sensors or different information, it might be beneficial. So what we can gather from this, it might be beneficial to actually first check if there is a big difference in informativeness between the sensors, because that will bring the biggest change in cost. And if not, then actually including more sensors in your model, which then means you actually increase the complexity of your model, then that benefit of reduced cost might actually not be worth the extra complexity of considering more sensors. And according to what we see here, it's actually beneficial to, in most cases, just stick with one external sensor source, depending on what you have. So that is the work that we did here. And basically, if we look back at our question, we were really motivated by asking the question, do we need more data? And if we do, when do we want access to this data? And in the work, we could show that the optimal policy consists of at most 4 regions. And we could show when is a decision maker actually willing to pay more for external information, and when should you forego that information and save costs. So thank you very much. And if there are any questions, I'll be happy to answer.
Well, thank you very much, and consider this a virtual clap. I can clap here. I actually have a ton of questions. I find this very, very interesting. But let's first see, are there any other questions from the audience?
Yes, Pierre, thank you very much for this very interesting presentation, which is basically about the value of information and how you can take that into account in decision making. I guess, at least from my point of view, the most difficult point is to estimate the conditional probabilities of the various states given the observations. So how do you deal with this uncertainty? What if instead of having a value for the conditional probabilities, you had a range? Would that how would that modify your policy making algorithm?
Yeah, thank you for your question. So just to make sure I understand, so could you just explain what you mean by range of condition probabilities?
If instead of being sure that when you observe, when you use sensor 2, the probability of having a healthy condition is, let's say, 0.66. Yeah. Instead of that, if the probability was between 0.60 and 0.70, and same thing with the other ones.
Yes. So okay. So that's a relevant question. I would say for our specific model and implementation, we would still need to change it into a discrete matrix. It does rely on that, but if usually to obtain these matrices, so we used a hypothetical example, but if you have data from a machine, different observations, you can actually, typically for this approach, to get those observation matrices, you would use hidden Markov model techniques such as the expectation maximization algorithm that would output discrete results as your observation matrix. So that's one example that you could use. Or I would say if you have a range, then you could look at the probability distribution for that range and choose an average for that observation. Or even use clustering algorithms to get a specific value and then put it into a matrix. But yes, ultimately for our MDP to work, we need a discrete state observation matrix.
Yeah. So basically you could take perhaps several discrete values and then it leads you to a range of curves. So that these curves will be a band, family of curves. And then at some point the decisions will be affected by that uncertainty, of course.
Yes, and the more reliable the technique that you can use to get the more reliable state observation matrix, the better. Yes.
Of course. Thank you very much.
Anytime. Thank you for your question.
If I may actually follow up on that, so I think the model that Pierre was referring to is called an uncertain MDP or uncertain POMDP, where you have not concrete probabilities or point estimates, but you have ranges or intervals of probabilities. And we had several works on that. So the task is then to compute a policy, in that case a maintenance policy, that accounts for the worst case that can happen within these ranges of probabilities. And the solutions are based on robust convex optimization. I'm happy to send them, Pierre, if you're interested.
Oh, great. Yes, thank you very much. Thank you.
I was just, I recognize this, that there is often kind of that works are not known that go over the areas, right? So this was more we published in the AI area. Of course, this is different here. Okay, any other questions?
Yes, I had a question. Thank you for your presentation. And what I was wondering about is, so I've read your paper partially. You restrict to 2 states, right, for the belief space. What's is there a clear reason for that?
Yes, okay, that's a relevant question. Yes, the first reason is tractability, and also it allows us, by having 2 states, it allows us to present the results by means of the control chart that we saw earlier, where as soon as the threshold changes, we can change our action, simply because our belief state only consists of healthy or warning state. So, and we define the belief state as the probability of being in the warning state. So 1 minus that is our probability of healthy state. So if we were to have more states, then the dimensions of our problem naturally will increase. And with that, the visualization of the problem will also be different. But for us, when we decided to stick with two states, we could, because it's the main necessity for that is you want to know when is it close to the warning state. So even if we believe there are more than 1 healthy states, we could combine that as 1 healthy state for this model without necessarily large losses in generalization, and still get the result of when do we maintain.
Okay, that's clear. Thank you.
Okay, great, thanks.
There's a question. Please just unmute yourself.
Yeah. So I would like to have some question because it's very interesting field for me. And more about deep learning and machine learning with these more applications. So I learned that through your presentation that you use Markov chain model to model the state and to detect if the additional information can really help to improve the to detect the state, whether it's go into warning or it is healthy state. And the thing I consider is the Markov chain model can only consider the historical data in the case step, so only 1 step back. So for your application, do you think that if you also consider the historical data in the n step back or k step back into the past, it would is better to filter out the unnecessary data, or invaluable data, or just consider only 1 step back into the past is enough to filter the data or to select the data?
Yes. Oh, thank you. Thank you for the question. So if I understand the question correctly, basically the value of a POMDP is that the belief state, it has been proven analytically that the belief state, which is the probability of being in a warning state, actually considers the entire history up to that point, while still preserving the Markov property of memorylessness. So that belief state includes all the updates and all the observations we have observed up to that point to determine it. So I hope that answers your question.
Yeah, but that is also one drawback. So people thought that the Markov chain can inherit all the information in the past of the case step back, but actually it's only 1 because that is the principle of Markov chains. And as to make it clear, in this model, you use the hidden Markov chain, or you just use the model because I learned that you have the unobserved things. You have unobserved unobserved variables. So you use hidden Markov chain or just normal Markov chains?
So yes, so what we did to solve the problem is we took our POMDP, so with the unobservable states, and we translated it into an observable MDP in the belief states. So, and we did that then, and then we solved it using an MDP tool, solution technique. And what then meant, so our belief state that was continuous, we just discretized it into specific intervals, and that the belief states were then the actual states of the MDP, which then provides us with the results of the POMDP, if that makes sense.
But then you used discrete ranges of the belief space.
Yeah.
Okay,
yeah.
to get a finite representation of the belief MDP.
Yes.
Okay.
And yes, if you want more accurate belief states, then we just increase the interval.
Yeah, okay, thank you. Yeah.
Okay, any other questions?
I have a question, if I may. My name is Berend Jan van der Zwaag. Sorry, I have no camera. Thanks for your presentation, Heletje. Very interesting, especially from the sensor side, which is usually my background. But I was wondering at the other end of the spectrum here, where you have now, basically at the high end, you have the maintenance region, right? But I was wondering, what if you also include something like a failure region? Sometimes you have like a sudden failure, where you basically have no time anymore to do any preventive maintenance. If you would include something like that, how much would that actually change the model? Would it have any influence at all?
Yes. So
because that usually comes with a very high cost compared to all the other costs that you have, right?
Definitely, yes, definitely. That's a very good remark. So basically, we do include unexpected failures in the model. So if we look back, maybe I could even quickly go back to it. And I may have not necessarily touched upon it. So
yes, I see.
Yeah. So if a machine fails, we assume we're not even going to take an action. We're going to immediately maintain the system. And this formulation works because in one sense, without loss of generality, we assume maintenance actions are instantaneous. And we make that assumption because we actually model, I don't know if I neglected to say this, but we model the problem, the time horizon, in running hours. So if a machine fails, we believe it stops. And then effectively time also stops because running hours stop. So then we immediately perform corrective maintenance and we continue on optimally after that, and the running hours continue.
Yeah, probably you mentioned it, but I may have missed it more looking at the pictures than the formulas. But it's a relief that it is in there somewhere, so that it is actually a part of the model.
Yes.
Thank you.
Anytime. Thank you. Thank you for your question.
Any other questions? Okay, then it's my turn. Thank you again for this very nice talk. So I work on POMDPs more on the algorithmic side from the AI perspective. So of course this is extremely interesting to you. And my first question was already answered because I was asking how you actually solve the problem. I mean, it's obvious it's in general an undecidable problem or very hard if you have some restrictions, but this discretizing of the belief spaces is a common technique. By the way, there is extensive tool support in the AI community for these things that I don't know if you use it, but that's definitely true. So what I wanted to say is a few things. So first, you have kind of a mixed observable setting, right? So you have certain variables that are observable and others are not observable. People have looked into how to solve these more efficiently. if it is interesting for these are called MOMDPs, mixed observable MDPs, where they really look at the underlying structure of the system and exploit that to solve it. But my actual question was a bit related to Pierre's question. So you assume these probabilities that you have, but how do you get them actually? This I didn't get in your talk.
Yes. Yes. So in this paper, we did not explore how to get the probabilities, but in other work we did. So basically, I would say to get the probabilities, again, as mentioned previously, I don't know if that would be the best approach, but I would again use hidden Markov model techniques. So you take the data, you put it into your expectation maximization algorithm or similar, and find the probabilities, and perhaps check that, or always check that with a domain expert, and yeah, work from there.
Yeah, that I guess that could be an option. So what we are working on is more in the direction of reinforcement learning, where you basically explore the system by taking certain actions, if you do have access to a simulation environment, and then use the outcomes to infer probabilities more in a Bayesian way. But I guess it would be very interesting to actually discuss a bit on how several parts could work there.
It would, definitely. And I think the benefit of your work, if you would use reinforcement learning, is we do impose a specific machine behavior. So we do, for our model to work, we do need to assume it does follow at least a specific distribution. It is Markovian.
Okay.
And I believe for reinforcement learning, you would not need to make such strict assumptions.
Yeah, that's very nice. Yeah. One idea I had when I was listening, so you have this external sensor information, which is modeled as a people would call perhaps a parameter, hyperparameter, variable, or whatever. And would it be an interesting problem to basically to keep this as a variable and then try to find a solution to an optimization problem that computes the best desired trade-off between optimality of the maintenance policy and perhaps the low cost of the sensor. So could this be interesting? I mean, you did this basically by trying out several values, but for a more complicated setting, if you had a rhythmic way to find kind of the sweet spot between these trade-offs, would this be interesting?
I think yes, definitely. I think especially, so I'm not in industry, but if I were to be in industry, I think that would be something I would like, because usually the feedback when we talk to companies about this is they really want to keep it as simple as possible. They want 1 or 2 thresholds. As soon as we increase the thresholds, then it gets complicated for them, because they don't have to just maintain 1 or 2 machines. It's normally a large, very large installed base that has to be maintained. And then to follow 4 or 5 different thresholds is not necessarily ideal from a practical perspective or implementation. But if you could analytically find the trade-off and then perhaps take it further and determine which trade-off does provide the most value for the cost, then at the expense of maybe 1% higher maintenance costs, then I think that is probably the solution that would be implemented.
Yeah, very nice. You could also have like a finite number of options for these sensors, and they may be implemented in various combinations, and then kind of determine the optimal or near optimal, if you want it fast, configuration, right? So these, I've always looked for applications for such settings. We have some work in the past with a rather artificial case study, but yeah, this sounds very, very related. This is my questions. I would send you a follow-up. I find this extremely interesting. And so is there another question from the audience at this point? There is one.
Yeah, first I just want to follow your questions. about how to find the probabilities. So it is quite difficult when you have an observed variables. But also in practice, also maybe it's almost very difficult to get the real sample. So you might want to consider the Gibbs sampling. So when you use the Gibbs sampling at the Markov chains with like Monte Carlo's methods, then it might improve the way you can optimize this one. Yeah. So it's a Gibbs sampling. It is. Did you know it?
No, I've actually not heard of that before. But yeah, I would like if you can share about it. It would be I would be happy to look at it. It sounds like it could make a good contribution when you think about how to get observations.
Yeah. So I type it in the chat for the spelling. So.
Thank you. As soon as I stop sharing my screen, I'll look at the chat. Thank you so much.
Yeah.
At least I am not able to see the chat because I'm not a University of Twente member. So
so GIB is a GIBBS. G for green, I for green intelligent, and BB is B for bachelors, for example. BB and S for super.
Right. Thank you so much. Thank you. I'll definitely look into that.
Yeah. So it would help you with how to collect an observable sample.
Okay. Any other questions? If not, I guess we can conclude. Thank you again very much for this very nice talk. So I guess this was very interesting to the whole audience, and particular to me. I can attest for that. So thanks for doing this for us, and talk to you soon. And to everybody else, goodbye. Have a nice, now you can say evening, and see you all soon, hopefully next time in person. So, goodbye.
Goodbye. Thank you so much, Niels, and thank you, everyone.
Goodbye, and thank you for that.
Goodbye, and thanks.
Bye-bye.
But yeah, Niels, I think it would be interesting to reconnect. You sound, the information, like the uncertain PONP and the mixed observable you've shared, I've actually not come across that. So if you have interesting to share.
Yeah, it was quite funny when we started up the PrimaVera project. I met Rob Buston for the first time, and I think he was in your committee or something like that. And we accidentally, some of us dropped the word POMDP, and I really didn't know that operations research people were really working with POMDPs, and he didn't know that we were really working on the algorithmics behind it. So this was quite interesting, and I think this is very fruitful to speak, because I think that most case studies for POMDPs that are around in the literature are so simplistic. This is it's often just these funny grid worlds where you just move to another corner and something like this. And I've seen in Rob's work, on the other hand, that they don't know a lot of algorithmic how to put it, innovations that have been done over the last years, which would just scale these up to millions of system states, right? So to really make it more interesting also for industry.
Yes.
And
Yes, and we, like, even myself, like this, it's a very simple model. It's easy to solve. So yeah, it wasn't necessarily necessary to look into complicated methods, but indeed, I think we also shy away from the complicated, from bigger models, because we don't necessarily have the tools.
So the thing is, these tools often they're just easy to use. The only thing is they need a specific input and specific input language. But this is a barrier which is usually easily overcome. So two of my PhD students are now working with a student of Rob to actually get one example of them to our tool chain. and yeah, and we could do the same or just discuss. I mean, what is there? Also, yeah. Well, so these uncertain POMDPs, this was quite nice line of research, and it really came up because somebody asked me the same question as Per asked you. So they asked, what would you do if these probabilities are not precisely given, which might be just unrealistic? And then I thought, no idea. And so we started thinking about it. Yeah, I'll follow up. I just sent you an email, and perhaps we can just have a chat and then see where this can go.
That would be so great. Yeah, because I'm also working on with another colleague on a POMDP in kind of dual sourcing setting. So, and that does seem like it might blow up a bit. So it would be definitely valuable if to talk to you. Yeah, and I'm very happy to also if there's interest to help a bit. I mean, there are some students who could definitely help with setting something up. It's just it's not that much work if somebody knows the inputs and how to use the tools. Okay. Awesome. Hey, thank you very much, and hopefully see you soon. Yes, definitely. Thank you for the opportunity, and yeah, I'll definitely be in touch as well. Cool. Sounds good. Hey, bye-bye. Bye, Niels.